All right, hello and welcome to our snow day edition of Math 336 when we're going to finish up our discussion of concentration problems. So welcome to my third floor of my house and makeshift office. So let's just pick up and let me make sure this is actually recording. Looks like it is. Okay, good job. Here we are where we left off last time, right? You have the concentration extra problems, extra file online, so I'm not going to write out any of that stuff. It's all there. This is sort of where we ended last time. We never wrote down the formula for the volume, and that is kind of where you have a much more general approach to these problems. A lot of the classic problems that are in most textbooks don't require the formula because, you know, these input and output flows are constant. But if those input and output flows are not constant, then this is just a much more general idea and process for more consistently solving these types of problems. So let's look at one of the problems in your textbook as an example and set it up in the context of this particular process here. So this is example 1.4.2, right? And so remember, what are we saying here, right? That the rate of change of amount with respect to time, amount of some substance, right, is equal to, well, some input flow rate, right, times some input concentration, minus some output flow rate, times the 1 over the volume. The volume has this expression, so this guy is V of t, right? And x is your dependent variable. X is a function of t, right? And so x of t over v of t is really the output concentration, the concentration at any time t. So it's really FICI minus FOCO, right? Okay, so we already talked about all of that, but let's just look at it in the context of this problem, okay? So in this problem, we have a 100-liter tank contains, and I'm not going to draw out anything, it's all in your book. A 100-liter tank contains 10 kilograms of salt dissolved in 60 liters of water, solution of the water and salt, concentration of 0.1 kilograms per liter, flowing out at a rate of 5 liters per minute. It's just a bunch of words, right? Unless you're really just focusing in on what you're being told. All right, so what we're being told here, right? Solution, let's look at that sentence. Solution with a concentration of 0.1 kilograms per liter is flowing in, right? So what does that tell us, right? That CI is 0.1 kilograms per liter, right? Is flowing in, FI is in at a rate of 5 liters per minute, right? 5 liters per minute, yes? Okay? So if I think about Fi times Ci, right? Fi times Ci, that is going to be 5 liters per minute times 0.1 kilograms per liter, right? Concentration, flow rate, and what are we left with, right? 0.1 times 5, right? So 0.5 what? Kilograms per minute, yeah? Okay? And that is good because our amount, x, right, is measured in kilograms and our time, t, is measured in minutes. And so every term in the equation has to have units of kilograms per minute. So this product, FICI, is going to be 5 times 0.1, right, which is where the 0.5 comes from. Yes? Does that make sense? And this guy is also in kilograms per minute. Okay? All right, and then minus what? Okay, so now we want to know the output. What is left to figure out? F0 and V, right? 1, 2, 3, 4. Those 4 things are the things that need to be determined, yeah? And then you have your differential equation because this guy is your unknown, right? Okay, so what is F0, right? F out, sorry, not F0. So the output flow, the flow rate, what does that say? The solution in the tank is well stirred, right? All these idealizations that makes these nice and continuous and allows us to use these differential equation models to talk about X at any time t, the amount in the tank at any time t, but not have to worry about where you are in the tank, right? Okay, so it doesn't matter where you are in the tank, everything is well stirred enough so that that describes the amount in the tank at any time t, regardless of what position you're in the tank. All right, otherwise we'd have a PDE, right? So flows out at a rate of 3 liters, right, per minute, okay? Yeah, and so that means we know that this guy is 3, right? And then the question becomes, what is V? What is the volume? And now you can get a little bit confused here if you just start reading stuff. A 100-liter tank contains 10 kilograms of salt dissolved in 60 liters of water. Okay. There's a lot of liters in there, right? Liters is our volume measure. And the biggest mistake students make is using the wrong thing for V, okay? So let's think about this. You have a tank that holds a maximum of 100 liters, but what are we told? There's 10 kilograms, well that's an amount, right? So we're gonna ignore that for right now. It's dissolved in 60 liters of water. So this equation says the volume at any time t is equal to the initial volume, that's V naught, initial volume. Well, what is our initial volume? We're being told that this tank starts with 60 liters of water, right? Okay. Plus, now, you know, for these problems, you have to be like slightly clever to figure out what V is. And if these guys aren't constants, then good luck, right? But here, we're taking the cleverness out, right? You just got to identify everything and evaluate the formula. So the initial volume, the initial amount in the tank is 60 liters, yeah? So V naught is 60 liters. And again, the units have to make sense. It's a volume, right? Liters is a volume measure. And then we're going to just to determine what should go here, right? So F0 we know is 3, and then it's going to be 1 over something, and we're not sure what. What goes there? Well, we're going to just evaluate this expression with calculus, right? So what do? We're going to integrate, right? Add up all the flow rate that's coming in with respect to time. What is Fi? It's 5, right? It's a constant, Fi of S. We're integrating from 0 to t, adding it all up, right? And so if this flow rate depended on time, right? If it depended on time t, then you would change that t to an s, because this is a integration like those we've been talking about in this class recently. All right, so this guy's Fi is just 5, right? ds minus the integral from 0 to t, the output flow, right? We're adding up with integration all of the outward flow. Notice, right, this has units of liters per minute. I'm integrating with respect to minutes, right? Liters per minute times minutes is going to put out liters, right? Because I'm integrating in time, yeah? From s equals 0 to s equals t, some unknown time. So this is 3 is what's going into here. It's a nice constant, right? So it's not some function that I have to evaluate in terms of s now. And I have this nice little expression then, okay? And so it's super simple now for me to do this integration, right? I've got 60, now I can do each one separately, yeah, or I can recognize from my rules of integration, right, that since I have the same integrands, 0 to t, it's just the same as 5 minus 3 ds, right? Integrating that, and 5 minus 3 is just 2, right? So 2 ds, yes? Okay? And so what do I have? 60, and just to make sure we're all like aware of what's going on here, I'm going to integrate 2 with respect to s. What do I get? 2s, right? Then I'm going to evaluate that between s equals 0 and s equals t, fundamental theorem of calculus, right? And so then what? I've got 60 plus, what do? Right? Plug in t for s first, right? That guy goes in first. 2t minus, fundamental theorem of calculus says plug in 0 for s. Yeah? And so lo and behold, we get 60 plus 2t, which is what needs to be used for the volume. And you didn't have to be clever to figure that out. You're clever because you understand that this is going to determine the amount of volume. When we take the initial volume, add up everything that came in and subtract away everything that came out over the interval from time 0 to time t, right? That's going to be the volume at any time t. So that's awesome. And now, right, we're done, right? Here's our ODE. So remember, x is our dependent variable, t is our independent variable, and notice, right, this guy had units of liters per minute, and this guy has units of liters, and this guy has units of kilograms, and so again, it's kilograms per minute, right? Okay, this is liters, right? Because it's volume, yeah? And so the units work out properly. So how do I solve this ODE, right? Now I've got to write it in the appropriate linear form, right? Remember, our linear form says get everything with the dependent variable on the left-hand side. So I've got dx dt, right? Bring this across, plus 3 over 60 plus 2t times x is equal to 0.5, or 1/2. Well, let's just use 1/2, right? Okay. Okay. Are we good? And here's our equation, right, which is now written as the derivative of x with respect to t plus some function p of t times x is equal to some function q of t, right? So this is exactly what we did last time, except for x was our independent variable, right, and y was our dependent variable. And so it doesn't matter what the letters are, you still have to be able to acknowledge and recognize what you have, okay? So here's our ODE, okay? This is our ODE. And if we were just gonna, we'll come back to the initial condition later. If we're gonna solve this guy, right, then what was the idea, right? We needed an integrating factor. What was the integrating factor? U is e to the integral now of p of t dt, because t is our independent variable, yeah? And then what's the deal here, right? We multiply the entire equation by u, right? The left-hand side becomes u times the dependent variable prime, product rule, is equal to u, right, times your u of t times your q of t, and then you integrate both sides, right? That's what we did. So let's do that in this case for this specific problem, okay? So now we're going to identify our p of t, right? It's 3 over 60 plus 2t, yeah? And our q of t is 1/2, yeah? All right. And so now what did we need to do? We need to integrate p of t, right? And ignore the constant, we saw y, and then raise e to that, right? So what is the integral of p of t dt, right? That's our question. So that's the integral, right? These are these guys, we need to know about that. So now we're over here. The integral of 3 over 60 plus 2t dt, right? Okay, well, you might need to do a v substitution, right? Don't use u because we already have a u there. So let's let v be 60 plus 2t, just to make sure we all know what we're doing. dv is then 2 dt, right? Okay, so what is dt? dt is 1/2 dv. Whoops, did that look like a u, right? 1/2 dv. And now we can sub in here and get precisely what we want. So let's come here. I hope you can still see this. dt is 1/2 dv, right? So I'm going to get a 1/2. I'm going to stick the dv out there. Yes. dt is being replaced by 1/2 dv. And then I've got 3 divided by v. Yes? I'm going to just double check and make sure you can see that. Pretty sure you can. Yay. Okay. And so what do we have here? We've got 3 halves the integral of 1 over v dv. We're so good at this integral now, yeah? 3/2 times the natural log of the absolute value of v, yeah? Okay, plus c, but we just said we don't need that because we're doing an integrating factor integration. That's what we're integrating. And so what do we have? 3/2 the natural log of the absolute value of 60 plus 2t, which was our, sorry, that plus looks like a times, 60 plus 2t, I don't want to fall down the stairs here, which was our v, right? Okay, well now 60 is positive, t is positive, this is a physical problem, right? Time, t is time, and so 60 plus 2t is positive, and so we can say 3/2 natural log of 60 plus 2t without the absolute values, okay? So that is our integral of p of t, right? So that's what the integral of p of t turned out to be, 3/2 natural log of 60 plus 2t, yeah? Just kind of doing this problem that's done in the book just to make you see it slightly differently, because the notation there's a little bit different. Okay, so now what do we do, right? So our integrating factor for this problem is u is equal to e to the integral of p of t dt, right? Well, we just did the integral of p of t dt, so what is u? It's e to the what? 3/2 natural log of 60 plus 2t, yeah? Okay, well that looks kind of ugly, but this simplifies, right? What do we have to do for that to simplify? Yeah, super close, right? E and ln, but the 3/2 is in our way, yeah? So what property of natural log do we want to use? Yeah, right? A times the natural log of b is equal to natural log of b to the a, right? Yeah, that guy comes up. That property makes our life better. And so we're going to take this guy, a times the natural log of b, we're going to bring that up here. So then we have this is e to the natural log of 60 plus 2t, all raised to the 3/2, yeah? And now we're in shape. E and ln undo each other, nice inverse operation. And so what does our u turn out to be for this problem? 60 plus 2t to the 3/2, right? So hopefully you see a little bit better where that came from. Again, remember they call their integrating factor r of t, okay? So now that we have the integrating factor, what do, right? Well, it's this idea, right? You multiply both sides of the equation by the integrating factor, and when we do that, the left-hand side becomes a product rule of the integrating factor. So multiplying by the integrating factor right? It's a factor that allows us to integrate, right? Multiplying by the integrating factor, our ODE that we had, the left-hand side becomes just the integrating factor, which is 60 plus 2t raised to the 3/2 times the dependent variable, which is x, right? In this problem, in concentration problems, oftentimes x, right? That's okay, you can live with x as a dependent variable. So when I do that on the left-hand side, I get this product, the derivative of that product has to equal this product, right? What was q of t for us? It was just 1/2, the non-homogeneous thing on the right-hand side. So it's just 1/2 times this, right? So 1/2 times u, q of t times u, right? 1/2 times 60 plus 2t to the 3/2. Now we won't even think about trying to bring that 1/2 in there and divide it out, right? You can't do that. Okay, good, good, good. All right, so now we're there, right? So that was our idea. You determine the integrating factor, multiply the original equation by the integrating factor. The left-hand side becomes a product rule that's nicely written as the derivative of this product. And then we just solve, right? So I'm going to erase this over here as well. Give me some more space. And now you go ahead and solve, right? And so if I'm going to solve this equation, this is a derivative with respect to t, right? Okay, and so I should have left myself more space. So if I'm going to solve this equation, I'm going to put it in here in blue. I'm going to integrate, right, with respect to t, this, and then I'm going to integrate this with respect to t. Yeah? Okay, I'm not going to do much more of this problem because the rest of it is in your book. But when I integrate that with respect to t, right, this is a derivative with respect to t, d by dt of this expression. What do I get? Just the expression, right? 60 plus 2t to the 3/2 times x, right? This x, remember, is our x of t that we're looking for, the solution of our differential equation. And that is equal to this integral, okay? Okay, let's just do it. So again, here, if you use the exact same integration, 60 plus 2, v is 60 plus 2t, dv is 2 dt, right? So dt is 1/2 dv, yeah? Oh, I wrote it as u again. All right, so dt is 1/2 dv. Then if I am going to replace this integration, right, dt is getting replaced by 1/2 dv, yeah? So I like to put my dv out here, right? So then I'm going to have another 1/2. 1/2 times 1/2 is going to be 1/4, right? I'll just bring that out there, yeah? And that's going to be 1/4, and then what do I have? V to the 3/2. Oh, I put that way too far out. Okay, 1/4 the integral of v to the 3/2. For some reason, I don't think it's like a bad idea to just make sure we walk through this. Okay, so are we good there? Yeah, v to the 3/2 dt is 1/2 dv. We're good. All right, what is the integral of v to the 3/2? Add 1 to the exponent, divide by the new exponent, right? So what do I get here? 1/4, multiplying constant, add 1 to the exponent, v to the 5/2, divide by the new exponent, so multiply by 2/5, yeah, okay? And then don't forget your plus c, right? Okay, we all understand why we don't have to multiply c by 1/4. Okay, good. So now let me come back up here. So here we are. So what do we have? Just coming right up here. So we have that 60 plus 2t to the 3/2 times x, right, which is our dependent variable, our unknown we're looking for, is equal to, well, 1/4 times 2/5, right? So what do we got? 1/10, right? Yeah, 1/10, right? V, oh, we never went back to what our v was. Whoops, that was bad. Okay, so let's just do that. 1/10, what was v, right? V was 60 plus 2t, 2. So right, we got that to the 5/2, right? Plus c. So I guess I'm just rewriting down the same thing. 60 plus 2t to the 5/2 plus c, right? And then finally, what is my goal? My goal is what is x of t, right? That means I'm just solving for that guy. So x as a function of t is, I just divide by this guy, right? Or multiply by that to the minus 3/2, right? And if I do that, I've got to do that with both terms, yeah? And so when I do that here, I'm going to get 1/10 dividing 5/2 in 3/2, same term in there, right? That's going to give me 60 plus 2t to the 2/2, yes, which is the same as 1, plus c over, right, 60 plus 2t to the 3/2. Here is our x of t, okay, for any time t. And now that solves the ODE, right? You can compare that to the solution process in the book. I just like this better. I just think it's simpler. Anyway, what else do we need to do? We need to talk about the initial condition, right? What is the initial condition? Okay, well, there's still some numbers that we haven't used in this problem, right? In this word problem. A 100-liter tank contains 10 kilograms of salt. dissolved in 60 liters of water. What did they just tell us? What do we, for an initial condition, right? Our dependent variable is x, our independent variable is t, x of t is our solution, so our initial condition needs to be x evaluated at some t naught, right? Or x at 0 in this case, right? Doesn't always have to be 0. X at 0, what are the units of x? What are the units of x? Kilograms. Good. That helps you determine what piece of this information that you've been given is actually some other thing that can be used as an initial condition, right? Okay, so what is it? Good. It's the 10 kilograms of salt was dissolved in the 60 liters of water initially. So x of 0, the initial amount of salt, right? The initial amount of the substance, the amount of the substance here is the amount of salt at any time t in the solution. So the initial amount is 10 kilograms. Yes? Okay? Units make sense, right? And so now you can just solve for C by plugging in there and double check you get all the same things that you see when you go to the solution in the book. Okay? What else should I mention before we look at one more problem? So that's the process for solving any one of these concentration problems. The critical thing is, what are the input flow rate, the input concentration, the output flow rate, the volume, which you calculate this way. So what is the initial volume? Paying attention to units, if you wouldn't confuse what to put here with what to put there, right? Kilograms and liters are totally different, yeah? Okay, and then those four things, right? This one only requires this number, and you've already figured out those two guys, and then you do that integration. Then you know what to put in your ODE. Then to solve your ODE, you bring that piece across, and then you use the linear process, right? Okay? The only other thing you need is an initial condition, and that you have to scour the word problem to determine what is the appropriate initial condition based on what your X stands for, yeah? And again, your units help you. The other thing to pay attention to, or just to be aware of, is what is concentration at any time t? Well, that's just, we'll often call it C of t, but that's just X of t divided by V of t, right? It's amount per volume, right? Kilograms per liter, yeah? Okay? And so you can't say what this is if you need to know the concentration at any time t. Well, then you first have to solve for X of t, right? Okay, and then determine C with your initial condition, right? And then you know X of t, and then what is the concentration? It's X of t divided by whatever you found V of t to be here, right? And for us, that was 60 plus 2t, yeah? Does that make sense? So if you're asked about concentrations, right, at any time t, then after you solve the problem, you got to take your solution for X of t and divide it by what you found V of t to be, yeah? What else did I want to mention here? The other number that's in this problem, 100-liter tank, is necessary for the question about how much salt is in the tank when the tank is full. How much salt is in the tank when the tank is full? How much salt means what is what letter? Good. X of t, right? What is X of t? Right? How much salt? That's a kilogram measurement, right? That's an amount of substance, okay? What is X of t when, how much salt? What is X of t when what? When the tank is full. When the tank is full, well, what does that mean, right? When V of t equals 100, right? They told you it's a 100-liter tank, right? Okay, you have a formula for V of t. V of t is 60 plus 2t. Then you have to solve that for T and determine at what time is the tank full, or at what time would the tank overflow, right? If the inflow is greater than the outflow, at some point, this tank is going to overflow, right? Yeah, if you keep pumping stuff into it. And so at what time would it overflow, right? So how much time do you have in your chemistry experiment to go run and get some lunch before you got to get back and there's a mess all over the place, right? Well, you can figure that out, right? Okay, so solve this guy for T, plug that value of T back into your solution for X, right? Okay, so the critical thing here, excuse me, the critical thing here that I really want you to kind of take home, we're going to look at one other setup of a problem, is translating the math, the words into the math, and not being afraid of the words, okay? And paying attention to the units helps you do that, as well as viewing the concentration problem formula this way. When you view the concentration problem formula this way, then you need only determine those particular things, right? Fi, input flow, Ci, input concentration, Fo, output flow, V naught, initial volume, right? And then you compute V of T from this, and this, and this, right? And then you just plug in, bring this piece across. And then you also have to figure out, right? You're going to have X at some initial time is equal to some initial value, right? Of X, right? And paying attention to units. This is your IC, right? Okay? What is T naught? What is X naught? For our problem we just did, T naught was 0 and X naught was 10, yeah? Kilograms. All right, so let's look at one more of these problems and just look at a setup maybe of the problem. I'll let you guys keep on going. Okay, so in this case, this is exercise 1.4.9, one of your homework problems. Let me just make sure, I just get like worried that this is not recording. Okay, it is. So this is one of your homework problems, and suppose there's two lakes located on a stream, right? So you got lake 1 and you got lake 2 and you got a stream, and the stream flows into the lake 1 and then it flows into lake 2 and then, you know, flows out. Okay, so this is what's happening. Yeah, okay. And so there's a whole bunch of information in here. Clean water flows into the first lake, then the water from the first lake flows into the second lake, and then the water from the second lake flows further downstream, and the in and outflow of each lake is 500 liters per hour. Oh, okay, we're happy about that, right? So what were we just told, right? Fi here, right? So we got a lake 1 problem and a lake 2 problem, right? Okay, right? So we got flow into lake 1 is 500, right, liters per minute, right? And flow in with lake 2, right, is also 500 liters per minute. Woohoo, right? Okay. Then what else do we know, right? So this is really a system, okay? We've got two things going on affecting each other. All right. The first lake contains 100,000 liters of water, and the second lake contains 200,000 liters of water, okay? So our V naught here is 100,000 liters, and our V naught here is 200,000 liters, yeah? Oh, and it says the outflow from each lake is the same as the inflow from each lake, okay? Now that's super awesome, right? Because what is this telling you, okay? This is telling you right here, if Fi is equal to Fo, right, and it makes physical sense, right? If the inflow and the outflow are the same, then the amount of volume stays constant, right? Okay? But it's straight here from the math as well. If the inflow and the outflow are the same, then if I subtract these two guys, I'm going to get 0. Yes? Okay? And if I get 0, right, then what do I know, right? So when when Fi is equal to Fo, right, identically, right, then that implies that the volume at any time t is just the constant volume V naught, and life is good, right? Because this would just cancel to 0, yeah? Alrighty, and so in this problem, V naught is just V of t, right? Because we have this same inflow and outflow, yeah? Does that make sense? Okay. It's quite possible you may see a problem later on where the inflow and the outflow are both functions of t, and then you actually have some integration to do to determine some other more complicated expression for V of t, okay? None of the book problems do that. They're all more boring, okay? Anyway, so let's see what else I wanted to mention to you all. All right, where are we? A truck with 500 kilograms of toxic substance crashes into the first lake. Okay, so now what do we know? Clean water flows into the first lake. How do we use this information, right? Okay, so clean water flows in, right? That's talking about concentration of our substance, right? So what is the substance? We don't really realize it until later, right? Where it tells us a truck with 500 kilograms of toxic substance crashes into the first lake. So really, right, what are we going to have? We're going to have an x of t problem here, and let's call it a y of t problem there. And what is x of t going to measure? X of t is the amount of toxin at any time t in lake 1, right? And what is y of t? Y of t would be the amount of toxin at any time t in lake 2, right? Okay, so this little piece that they gave us, suppose there are 2 lakes located on a stream. Clean water flows into the first lake. Clean water flows into the first lake. So we're flowing, and what is the input concentration then in lake 1? The input concentration for lake 1 is clean water, right? How much toxin per liter? Well, there's clean water going in, so that's 0 kilograms of toxin, right, per liter going in, right? CI is 0, yeah? What was the thing that they just told us? A truck with 500 kilograms of toxic substance crashes into the first lake. What is that? Well, that's a bad day for the truck driver, right? But what is that, right? What did they just tell us? The amount of toxin at time 0 when the truck crashes, right, is 500 kilograms. Right? That's an amount measure. Yeah, you know that, right? You know that this is going to be your amount, so that's your initial condition. Yeah? Okay. So, do we know everything we need to know for the X problem? I think we do. Okay? Let's see. So we know that these guys are V's, right? So we have our X problem. The X problem is going to be what? X prime is equal to Fi, which is 500, right? Times Ci, which is 0, yeah? Minus F out, right? Which is 500, right? Times 1 over V, which is just V naught for the reasons we discussed, which is 100,000, right? Times X, which is our unknown, right? That's the X problem. But 500 times 0 is just 0. So X prime is just negative, what do we got here? 1 over 0, 0, 5 over 1,000, negative 1 over 20x, right? What kind of differential equation is that? You can think about it for a sec. All right, what's our y problem? What's our y problem? Well, it's the same process, except y is now our dependent variable, right? T is still our independent variable, and y of t means the amount of toxin in lake 2, right? So I'm going to have y prime is equal to, well, what's the input flow rate for lake 2? It was still 500, right? What is the input concentration for lake 2? Okay, that's a question. What's the output flow rate for lake 2? It's 500. Yeah. What is the one over the volume for lake 2, right? Lake 2 volume at any time t is its initial volume because our inflow rate and outflow rate were the same. So that's that divided by 200,000, right? Times what? The dependent variable for lake 2, which is y. Yeah? So that's our y2 problem. We haven't quite figured out what CI is at this stage, right? So let's make this more simple. Let's just write this y prime is 500 times the input concentration for lake 2, right? The concentration of the toxin flowing into lake 2. What do the units of this have to be? Kilograms per liter, right? Yeah, that's the concentration. Yeah, okay. Is that one 0? Just like that one? Yeah, no, right? Because it's what's coming out of here is going into there, right? Okay, minus, just make this look a little bit simpler. Okay, what do we got here? 5 over 2,000, 1 over 0, 0, right? 1 over 40. Did I leave off a 0? 1 over 200? Yeah? Okay. 1 over 400? Yeah? Okay. Right? Yeah. Okay. Times y. Okay? All right. So this would, what is our, you guys tell me, what is our output concentration for lake 2? Yeah? What is the concentration of the contaminant coming in? Yeah, it's going to be the concentration leaving this guy, right? What was the concentration leaving that guy? It was x of t over v of t for this v, right? Yeah? Okay? So what's going in there is the concentration that's coming out of here. Yeah? So this is x of t over 100,000, which was the volume of x of t. Yeah? Make sense? Okay. So what do we have then? Let's take a look at what our problem looks like now. Oops, I didn't want to erase that. We've got our x of 0 is 500 kilograms. So what do we know? We've got a system now. X prime is minus 1 over 200x, right? And y prime is equal to, okay, let's see if I can do this math. Those two guys, 5 over 1,200, right? Yes, there we are. So is 1 over 200x minus 1 over 400 y. Yeah? This is a coupled system, right? Because the rate at which y changes depends on how x changes. Yeah? Okay, remember now x of t and y of t are our two dependent variables, two unknown functions. But the beautiful thing, right, about this system is it's uncoupled. Why? because you guys are so good at separable differential equations, right, that you can solve that guy by rewriting it how? Yep. Dx dt, that's what that means, right? X prime is negative 1 over 200x. And I will let you continue to solve that. You will be able to get a solution, x of t equals, right, plus a constant. You will apply the initial condition, x of 0 is equal to 500, to determine that constant, and that will give you a unique solution, right, for the x problem. And then you'll know what x is, so what will we do with that? Awesome. You'll plug it in here, right? And then this will be some explicit function of t, yeah? And so then what will we do? We'll rewrite this guy how in order to solve it? Y prime plus 1 over 400y is equal to 1 over 200 times x of t, whatever was the solution of the initial value problem, right? The explicit solution of that initial value problem for x goes in there. And then what do we have for our y problem, right? Now we have a linear first order ODE, whereas here this is also linear, but it's separable, and separable is easier, right? And so to solve our y problem now, right, what is our p? Our p of t here is 1 over 400. Yeah? And so what is our integrating factor for the y problem? And this is where I'm going to stop. U of t, right? T is our independent variable, is e to the integral of p of t, which is just 1 over 400 dt. Yeah? And so what is that? E to the 1 over 400t, yeah, or t over 400. We don't add plus c, we all know that, yeah. And then you proceed. You're not going to have a nice simplification that we got with natural log, because we don't have a natural log in that one. And so how do we proceed to solve this guy, right? You solve it by, it's pretty cool because I couldn't bend down like this not that long ago with my replacements. So here's our u, right? I multiply u across both sides. What do I get? E to the 1 over 400t times y prime, the product, the derivative of that product, is going to be equal to 1 over 200 times e to the 1 over 400t times whatever our x of t solution was to our initial value problem you already solved. And then you're going to do what? You're going to integrate both sides with respect to t, right? After you have something explicit in there, and you will be able to determine y as a function of t. You still need an initial condition for y of t. So think about that. What is y at 0? How much toxin, what is y of t? The amount of toxin at any time t. How much toxin was in lake 2 at time t equals 0? All right, that was lots of fun. Keep working on concentration problems. Use this formula, right? This idea of rate in minus rate out, what concentration is in order, and what volume, how to determine the total volume. Use the formula, use the calculus, then there's no guesswork, and it's more general for more general problems that may show up. What else did I want to say? Anything? Anything I missed mentioning to you guys? I don't think so. Don't be afraid of the words, right? Don't be afraid of the words. You just, oh, there is something I wanted to say. Don't be afraid of the words, number one. Pay attention to the units. They're going to help you, right? And let's look quickly more at what the questions were on that problem. So that problem asked you to find the concentration of the toxic subject as a function of time in both lakes, right? So what's that asking you to for? X of t over the volume for lake 1 and y of t over the volume of t for lake 2, right? Okay, two different concentrations, right? Okay, so you got to find y of t first and then divide it by lake 2's volume, which was 200,000, yeah? Which you can't tell from these pictures, right? This one's just deeper. You just can't see that. All right. Anyway, one of the next questions asks, when will the concentration in the first lake be below 0.001 kilograms per liter, right? So when is x of t over v over its v equal to 0.001, right? Find t, yeah? Such that x of t over 100,000 is equal to 0.001. Yeah, that's what that's asking, right? Kilograms per liter. You know, you're not just setting x of t equal to something. X of t is measured in kilograms, right? Kilograms per liter, concentration. Part C says, when will the concentration in the second lake be maximal? So let's just look at that for one sec. Well, you know from calculus that when you're asked for when something is a max, what do? Right, you want to take its derivative, right? So for part C of that problem, we want the concentration at time t for lake 2. That's going to be y of t divided by its volume, which was nice and constant. That made our life simpler. Okay, if this was a volume with respect to time, it'd be harder to take c prime, right? C prime of t, just because it's going to be, because this is just 1 over 200,000 times y, right? Is 1 over 200,000 times y prime, yeah? And if I'm looking for a max or a min, what do? I want to set that equal to 0, right? At what time t is that equal to 0? And then, if I want to know I have a max, then I want to look at the expression, right? Maybe I factored for y prime or c prime, right? Because 200,000 is positive, so the sign of c prime is the same as the sign of y prime. And what do I want? I want to get the derivative, either one of those guys, is positive before and negative after, right? Because if that's the case, then c or y would have to increase before and decrease after, right? That would have to be the actual behavior of c or y, right? Right? And if c prime or y prime is positive here, then c or y increases. And if c prime and y prime are negative, then c and y decreases. And so if I want a max, right, that's going to be at a place where the derivative is 0, yeah? And this is how I justify that I have max, yeah? And so you're just you will have already solved for y, and then you're just trying to determine this and justify our first derivative test, right? Yeah? Beautiful. We love calculus, right? Super fun, super awesome. All right, all for today. Have fun with your concentration problems. Hopefully you didn't have too much concentration problems with this video, but you can always stop, pause, come back. All right, see you soon.